Professor Vanden-Eijnden got his degree in Belgium, the University of Brussels, and after that, I think ever since, has been at the Courant Institute. That's an institute for mathematics at New York University. He has received a number of awards, including a Career Award of the National Science Foundation and a Sloan Award and several others. And I will ask you to join me in welcoming him to this presentation this afternoon.
Thank you, thank you, thank you. It's a pleasure to be here. I thought that there was here it is. It's a pleasure to be here. It's a bit nerve-wracking, actually, because I have, for two reasons, I have never spoken in such a beautiful surrounding, environment. I mean, this is really remarkable, this opera place, on one hand, and also I have my wife, my two daughters on the front row, which make things interesting, too. Okay, so, thank you. So, I will be discussing about extreme events, which are sometimes a bit of a misnomer and sometimes not. And I'm going to try to explain to you things that go from rogue waves to protein folding. In fact, I prepared two slides of introduction, title slides to show this. The first one is this one that you see here. It's a painting from Hokusai, who was a painter. He was born in the 18th century and he died in the 19th century. He was from Japan. And this is called the Great Wave. And it's often thought that it is a tsunami, which is one of these waves that come to shore after an earthquake. But in fact, it's more likely that it is what's called an okinami, which is a rogue wave, which is a wave it appears in the deep sea, out of nowhere, and can be damaging to ships or other structures, like these poor guys on the pirogues here. And part of the talk will be to try to explain to you what can one do to maybe explain or predict or even control wave of this type. But the title also contained protein folding, so I had prepared another little title slide. And this is depicting a little peptide, it's a drug, that's coming and docking into a protein, which is shown in the back here. And that's the way drug delivery typically functions. And the reason why this is not really an extreme event, it's more a reactive event, meaning that it's something that also involves a lot of thermal fluctuation, in the sense that these machines, these molecular machines, and we'll discuss that later in the talk, are not designed like the regular machine that we build. In other words, they take into advantage the fact that they work into something which is essentially an environment which is fluctuating, which is random. And I would like to explain that to you. Okay, so to begin, I mean, there's no better place to begin than the birth of modern science. And so let me introduce this character who you know is Galileo Galilei. He's the one who is credited to introducing the scientific method that led to modern science. You probably all know him. You know that he had a knack to get in trouble with the church at the time because he was insisting that the earth was not the center of the universe. He probably would get in trouble with the current administration too, because he was insisting on the fact that science should be based on facts, experimental facts, for that matter. And that led actually to modern science, because this was the point in history where science stopped to be natural philosophy. You had to have facts and experiments, and what you could, you tried to explain these experiments. That's what science was about, okay? And the year this gentleman died, another giant of science was born, and that's Isaac Newton, who introduced classical mechanics. And classical mechanics is essentially the set of laws that govern the motion of bodies, macroscopic bodies, but also microscopic bodies, subject to forces, like gravitational forces. And he introduces the law of classical mechanics, the three laws of Newton. You know them. I wanted to give a talk with no mathematical equation, but there is one I could have listed here. In fact, I don't even need to list it because I can say it, and you know it is F equal ma. That's him who introduced that. He also, understood gravitation, at least before Einstein, right? And his discovery, he also introduced calculus, for those of you who remember that from high school. And that has led, these classical mechanics, that's what Newton and mechanics is now being called, has led to essentially all of modern science and all of the body of knowledge that we have right now, that in particular explains celestial mechanics, including astrodynamics. I mean, we have been able to send people to the moon, or to send Voyager or Pioneer, these rockets to visit the solar system by following the laws of classical mechanics that Isaac Newton, who is depicted here at introduced. Here is actually Voyager 1, right? And to build microscopic structure, et cetera, et cetera. Okay? And so this was the body of knowledge at the end of the 19th century. The 20th century, as you probably know also, saw a certain number of scientific revolutions that in fact improved upon or generalized, if you wish, classical mechanics. One was quantum mechanics, which explained how things that happen at very, very small scales. Okay? And the other one were relativity, so the special relativity and general relativity, which were both introduced by Einstein, that explain what happens if either you have enormous bodies or they go very fast. Okay? And it was a new law of gravitation. But there was something else that happened in the 20th century, and that is more relevant for what I'm going to talk about, and that's chaos theory. Okay? And it all came about when, people took classical mechanics, and with that they could explain the motion of celestial bodies. And the first problem that they solved was, what if you have two bodies, the sun and the Earth, and they could calculate how these two bodies move around one over the other. Mostly there is the Earth that's moving around the sun because the sun is so much more massive. But then people said, well, I mean, the solar system contains more than two bodies, so let's try to solve this equation if we have three. And it clearly became clear that, in fact, the situation was quite complicated even if you put three bodies. In fact, nobody was able to solve this equation. And in fact, to this day, nobody really knows if, for example, the solar system is stable. It could be that at some point all will go. In fact, there's evidence that in ancient time there were more planets than there are now, and they've just escaped one after the other, and it become more and more stable, but okay, it could continue. And so people, like Poincaré, who was a French mathematician, and Birkhoff, who was an American, actually, Kolmogorov, who was Russian, realized, in fact, that there is a problem with this equation, or an issue with this equation, is that they can be extremely complicated because their solutions are very sensitive to small perturbation or imperfect knowledge in the initial conditions. Okay? You could take this, meaning classical mechanics tells you that if you know exactly the present, you can, in principle, predict all of the futures by solving the equation, which could be very, very complicated, but in principle, you could do it. The problem is that if you have only imperfect knowledge of the current state of the universe, so of your initial condition, then it could be that this small imperfection that you have, that knowledge, will make things diverge from one another. Your solution become quite quickly unreliable. And the person who actually really pioneered this idea and really was the one who founded chaos theory is Ed Lorenz, who is depicted here, who was a professor at MIT, but he was actually also an avid hiker, and he visited quite often Boulder and NCAR, the Center for National Atmospheric Research over there. And what he did was that he took advantage of the advent of computers, in fact, of the first personal computer, which is here, the RPLGP30, right, that he used to actually try to simulate atmospheric flows. Okay? This machine was, as you can see here on the advert by the company, was actually quite impressive because it was high-speed computation right at your desk. Okay? It has maybe it had 10,000 bytes of memory. And I mean, any one of your watch, and I'm not talking about your smartwatch, I mean, even the Casio that you have is probably more powerful than what this machine is. It also, needed 1,500 watts to operate, so you better have the cooling system in the room on top of it. It was like, you could open the window, etc. But he was using these machines, and what he realized was that he was trying to do simulation of atmospheric flows, and from time to time he wanted to save time. And so what he would do is that he would stop a simulation midway, take the initial condition and restart it and run two in parallel on two different machines. And to his big surprise, what happened was that he was getting solutions after a few hours that were completely different. Okay? So his first instinct was to say, well, there must be something wrong with this machine. I mean, it's overeating or something like that. But then he looked deeply into it, a bit more deeper. And what he realized, in fact, was that the machine was doing what it was supposed to do, but the computer, as you know, manipulates only a certain number of digits, meaning there are round-off error. It doesn't take all the numbers. I mean, it takes 14 digits typically. This machine actually was only taking 12 digits, I think, or maybe even less, but that's not very important for a story. And what happened is that when he was restarting the calculation, there was a little bit of an error in the 12 decimal. So that's very, very fast. It's a very completely tiny error. But after running the simulation for a few hours, he would get completely different states. Okay? And that led him, in fact, this was the foundation of chaos theories, as I said. And this was explained in this seminal 63 paper, where he coined the term of butterfly effect, right? Which, in fact, mean two things at the same time. One was that this dynamical system had an attractor which has the shape of a butterfly, and that's, these are if you look at the trajectory of what he was looking at in 3D, they look like a butterfly, as you see. But there was another meaning to the term, which was to say the flapping of a wing of a butterfly in Rio de Janeiro could create later on, a depression like a hurricane in, over USA. Of course, nobody can tell if that's really the truth. It's more a metaphor than real science. But it was based on the fact that, indeed, these systems are extremely sensitive to initial condition, right? And, well, I mean, in some sense, it's no surprise because, you have all seen this. If you look at, the plume, the smoke plume of a cigarette, which I've shown here, well, you can try as hard as you want by smoking 2 cigarettes to reproduce the same plume. You will not be able to do that, right? You will get that it will look more or less the same. It will, it will look a little bit like this. But if you look at it in detail, it will be different. And there will be no way, no experiment that you can conduct that will allow you to reproduce it exactly. And that's extreme sensitivity in small perturbation or in initial condition, right? And of course, the plume, the plume of smoke like this is not that big a deal if you can't really predict what's going to be happening. But this is Irma, you probably remember from last year, the hurricane, right? The same, is true with hurricane, which is that unfortunately we cannot really predict when they start how big they will be. Know exactly how they, where they will hit land, right? And this is an enormous problem, and that's something which is related, again, to this fact that dynamical systems are chaotic, right? It's a problem on the one hand, but also it made science much more human in a way because, it's clear that the celestial mechanics is very nice, but it's also very cold. It's, it's reversible. You don't see any. If you want to try to explain what is happening, most of the phenomena that are happening in our daily life, including the weather, but also biology, we're going to go to that later on in the talk. Well, clearly, you better have, a framework which allow for the diversity that there is in this system. Okay, and that's what chaos theory is about. And what it means, essentially, is that you need somehow to give up about the fact that you want to explain system on a really detailed basis, one by one. Because it's not only impossible, but it's also pointless, because you go too much into the detail. What you really would like to try to understand is things at a more coarse-grained level. In particular, you'd like to understand probabilities, which is, can you, for example, assess, giving an image, a satellite image of Irma when it was a smaller hurricane, the probability that it will become a category 5 or category 6 hurricane, okay, or that it will remain category 3 or category 4. That's the kind of thing that you'd like to do, okay? And in fact, there is a framework to do that also exists for quite a long time, that in fact was introduced before chaos theory, and this is due to Boltzmann, who is this, not cherry guys over there, who developed statistical mechanics, okay? And what he really did was essentially to use probability theory, which is, the theory that asserts probability, to try to describe the macroscopic behavior of systems that are made of many particles, okay? So what he actually did was he managed to explain, him and many others actually, how you can look at a microscopic system, like, for example, you can look at the molecule of a gas, for example, the gas in this room, right? And by looking at their motion, which is governed by classical mechanics, which is the law of Newton, you can try to understand concepts which are, in fact, in the realm of thermodynamics, like temperature, heat, or pressure, okay? And in doing so, what he managed to do is to kind of put on a firm, meaning first principle basis, the law of thermodynamics that had been introduced a little bit earlier, and that were in particular explaining the Carnot heat engine. That's the Carnot heat engine as you see it in the typical scientific book. And that's the Carnot engine that you probably are more familiar with. That is the same principle. It's essentially, oh, can you extract from heat or can you extract work? Okay? And so this was very useful because it allowed to explain phenomena like phase transition. Why do water freeze if you bring it below 0 degree? All the way to, indeed, engines like that. Okay? And because this will be very important for the rest of my story, I'll just elaborate a little bit on this by essentially explaining to you, in as simple terms as I can, how statistical mechanics allows us to see how microscopic order can emerge from microscopic disorder, and also something which is quite remarkable, or macroscopic irreversibility, meaning that there's an arrow of time, can emerge from systems that are microscopically reversible. If you look at F equal ma, if I were to show you a movie of two planets that orbit around one another, you would not be able to tell whether I'm giving them to you forward in time or backward in time. But if you look at the smoke, the plume, then you can tell what's going on. Okay, there's something which is fundamentally different. Okay, and so let me try to explain how all this come about with a model that was introduced called the Ehrenfest model. It's worthwhile remembering that there were two Ehrenfest on this paper, Tatiana and Paul, who is, sometimes remembered without her, but they were really both of them. And the idea was that, so what they looked at is the following experiment, which I could try to explain, with the room here. Suppose that I were to take all of the air of the room, I take a big piston and I would push all of the air of this side of the room compressed in the other side. Okay? You don't need to move, it's a thought experiment, I'm not going to do anything. But if I were to do that, and then remove this piston, well, you know what would happen, which is that there would be like a wind, then the air would go back and occupy the whole room, right? Now, you may ask yourself, how is that possible if what you're thinking about is that you have little molecules of gas that are going around in this room, right, with some velocity, kinetic velocity, which is related to, in fact, to the temperature that there is, and that for all practical purposes, you can think of being independent. It's not completely true. Air is actually not an ideal gas, but if it was an ideal gas, the phenomenon that I explained here would be exactly the same, which is that these molecules would move independently of one another. Okay? So how come if they move independently of one another in a very chaotic fashion, how come the air in this room is still, and you don't have fluctuation, where you don't have to worry that where you sit suddenly there will be a void appearing and you will not be able to breathe? Okay? That is never happening and probably will never. So the reason can be explained with this Ehrenfest, which is also called the dog-flea model, which is a very simple model, which is the following. Suppose that you have two boxes, and you have a certain number of balls that you place in these boxes. And then at any given time, you pick one of these balls at random in one of the boxes, and you put it in the other box. Okay? So it's called the dog-flea model for a good reason. This is what would happen if you had a dog with, with a certain number of fleas that goes next to a dog with another number of fleas, and they would kind of exchange their fleas, assuming that the two dogs are as likely to the fleas than each of them. So what would happen is this. You can just make a counting argument, and that's the basis of statistical mechanics, which is you can say, well, suppose, and you can think about these two boxes as really a virtual division of this room into two areas. Okay? And you can think, in how many ways can I put all of the ball in one box? Well, there's only one way. They all need to be in that box. Okay? And then you can ask, well, how many ways is there to put half of them in one box and half of them in the other box? So that means that each one you need to choose whether you will go on one side or on the other side. Okay? And if you do that, well, it's a simple little calculation that tells you that it is 2 to the power n. It's 2 times 2 times 2 times 2 times 2, n times. Right? That's roughly the number of ways you can do this versus the one way you can do that. Right? And then you can ask yourself, well, I mean, how many more configuration is this rather than that? By asking, well, let's take a typical n. Well, if n is 10, 2 to the n is about 1,000. If n is 20, well, 2 to the n is about 1,000,000. But the n that you have in this room is typically 10 to the 24. That's 10 with 24, 1 with 24, 0 behind it. So this number is astronomical. Okay? And so what is happening is that every configuration, if you wish, of the molecule in this room or the fleas in this box is as likely. But there's so many more that are roughly half-half that this is what you see. And fluctuations are impossible. If you ask yourself, what would be the probability that I take any, like, the surrounding where I am here, and that a void would appear, well, having no particle in here would be so much more unlikely than having particle that you never observe it. Okay? And this also explains irreversibility in the following way, which is that, well, clearly, this model, if I start with this configuration here, right, you can only pick a ball in the left box. So that means that you will pick one there, and the next trial, you're going to have a ball in the right box. Now, at the next trial, if there's many balls in this side and only one on that side, it will be much more likely that you pick one here and you put it on that box again. And this will keep going on until you have roughly half-half. Okay? So that means that for all practical purposes, if you start with a state which is out of equilibrium, that's the way we say it like this one, well, it will go towards equilibrium, meaning it will go to a state which is more like this. If you waited long enough, eventually, you would see this state reappear again. Right? This is called Poincaré recurrence time. Poincaré was the guy on the previous slide. But this time is astronomically large. And when I say astronomical, it's not even astronomical in astronomical term. It's more than that. It's millions of times the age of the universe. It would never happen if you have the molecules in that as here. So for all practical purposes, there's an arrow of time, which is that if you start with something which is out of equilibrium, for example, there's more molecule over there, or the molecule on this side are warmer than the molecule on this side, right? They will tend to homogenize in such a way that you'll have uniform temperature in the room if there is no heating and no other sources of heat or cold. Okay? And so that's the statistical mechanics. Now, this tells you something which is kind of important, and namely, it says that even though you can have something which is very disorganized, right, which is like I'm just assessing probability, every particle individually has half chance to be in either one of the boxes. It's very random. Right? Even though this is like that, there is order that is emerging if you have enough of them. Okay? And the theory that explains that, right, the mathematical theory that explains that, which in fact is the pillar of statistical mechanics, the modern pillar, the way we understand it nowadays, is large deviation theory. And we're going to use that in what comes next. This is still part of my long introduction to the topic. But the statistical mechanics essentially is, it's based on the fact that when a rare or an extreme event occur, typically they do so in a predictable way. Because typically they involve a sequence of unlikely events. Okay? And only one such sequence is essentially observable, because any other sequence is even much more unlikely that you don't observe it. Okay? It's the Vanden-Eijnden principle applied to physics or mathematics, which says that happy families are all alike. Every unhappy family is unhappy in its own way. Unfortunately, in this saying, the rare event is the happy family, because it requires all the right thing to fall, all the pieces to fall right for your family to be happy, and if anything fails, well, typically you're in the category of the unhappy family. Okay? And that's actually kind of interesting. So this is kind of illustrated here on this picture, which I don't know how illustrative it is actually, but it is to say that if you ask what is the probability to be in a region of phase space, as we call it, to have a certain event that occurs, and I'll explain that more in. So, well, even though the system could be anywhere, typically there's only one place you can find it, because any other place is too much more unlikely. It's like the molecules in this room are uniformly distributed, and this is the only place you can find it in normal conditions. Okay? And this is kind of interesting. I forgot to mention at the beginning of my talk, I'm not a physicist. I was trained as a physicist, but I'm an applied mathematician. And so what mathematicians do is typically to try to look at problems from an abstract level and to be able to transport things from one problem to another. Right? And this is the framework that we're going to use in the rest of the talk. I'm going to explain to you a certain number of things, but it's going to be always, in a way, this principle that will be applied to different systems. And so the third type of system that we're going to be looking at, and that's going to bring us back to the rogue waves, are extreme events in geophysical flows. Okay? So what are geophysical flows? Well, it's a kind of a generic term that essentially encompasses all large-scale motion of either the atmosphere or the ocean on planets. And it could be Earth, but it could be other planets, like, for example, Jupiter, but we're going to focus on Earth. Okay? And, well, this was the original playground of Ed Lorenz. This is the, typical, archetypical system, which is chaotic, meaning that, I don't need to tell you that the weather can be unpredictable. That's really, and this is not because people don't try to predict it. They do, but they fail because they have imperfection in their models and their initial condition. And this can have dramatic, well, annoying consequences if the weather is bad, or dramatic consequences, right, if you get a hurricane. In fact, here I list a few examples of events that can occur well, there are some like atmospheric circulation regime. This is the way the atmosphere flows, and typically they can be different regimes, and the way these regimes are, meaning the configuration of the flow, influence your weather, and it goes from one to the other. Okay. So this is important, but typically not crucial. There are other things that are already a little bit more important, like, for example, bistability of currents. Like the picture here shows a path of current which is called the Kuroshio. This is the south part of Japan, right? And you see the flow line of this current. Typically, it goes along the coast, and it stays in that state typically for a decade. But then in a matter of months, it can sometimes go for another few years in another state where from this small meander state, it goes into this large meander state, meaning that it takes a different path. And this is important because it changes the heat, the temperature, and the salinity of the water. And so, for example, it changes the fish population or where you need to go to actually fish these fishes. Okay? But then there are other examples that are, much more dramatic that also involve rare events, like heat waves, severe drought, extreme precipitation, rogue waves. That's the one we're going to be talking about in the next couple of slides, giant hurricane, etc., etc. And these I don't need to tell you that they are very, very important. I mean, I think that this year alone, the cost of the weather over the United States is in hundreds of billions of damages. Of course, it was a special year, but it would be better for us to be able to assess whether this is the new normal, or if it was really a special year. And so, we need to have models to assess the probability of these events. Okay. So I'm not going to be discussing about giant hurricanes or this, because typically this requires complicated model. I'm going to discuss something I've done research on, and which is also some sort, in my mind, a fascinating topic, which is the rogue wave that I showed you on my introductory slide. So what are rogue waves? Well, rogue waves are essentially waves that are much higher, so they are deep water waves, that are much higher than any other wave that you see in that sea in that state. Okay, so suppose that you have a calm sea, you could have a higher wave, so the waves are like this, there could be a higher wave that comes through. You could also have a rough sea, which is like there's a storm, and then there's a rogue wave that comes, and that one would be huge, because typically, right, so there is something that mathematicians call the standard deviation of the surface elevation. That's the typical height that you have, over the sea from crest to trough. And there's a rogue wave if what happened is that, this crest to trough exceeds twice the significant y wave, which is 4 times this standard deviation. So it's 8 times. So it's something which is quite huge. There's a picture here that show you why they are dangerous. So this is a picture which was taken in 1997 by the chief engineer on this tanker, right? But it's not completely clear that it satisfies exactly the definition that has been given by a oceanographer to a wave, but it was a big wave because this tanker here, right, is such that this deck is 25 meters, about 75 feet above water level. And as you can see, the wave submerged the whole boat. So the wave was higher than that. Okay, so it was really, and typically these waves come in triples. I'll show you that later. And so even if the boat takes one, then it falls into the crest and then there's another one coming, and that typically is the end of the boat. In fact, for a very long time, rogue waves were thought to be fable, that navigators were telling. And the reason why they were thought to be fable that navigators were telling is because there were no navigators that actually survived the waves. Right? So this would be the last thing you would have seen. But these days we can. Okay, so here is an actual evidence, scientific evidence of a rogue wave. And that's what you see is a time series of the surface elevation of an oil platform. Okay, so it's an oil platform that was in the North Sea, north of the coast of Norway. And as you can see, so, there was just recorded, you can see about that as a buoy, and it goes up and down, and it records just its altitude, right? And as you can see, well, it was a pretty rough sea. Probably was unpleasant to be on that platform. But at some point, it became really unpleasant because it was hit by a wave which was really huge. Okay? And here, this is the so-called Doppler wave. What you see here is just a zoom of the portion which is there. Right? And this was not, there were other instances that have been recorded. For example, this is another platform which is at a different place, but also in the North Sea. It's the Andrea wave, which, essentially a decade later, was hit by another wave, which was slightly less than this one. But as you can see, there was something quite remarkable, which is that even though this wave essentially appeared out of nowhere, if you look at the time series, they are fairly similar. It seems that there is something reproducible that is happening here. Okay? And so this essentially brings back what I was telling you about later on, which is that we can try to mathematize this or to try to understand. And the way to do that is actually to ask yourself, well, if I give you the current state of the sea, right? Typically that's random. So I give a snapshot of the sea at a given time and a given, say, location, right? For example, line, right? And then I ask, out of this initial condition, which is typically can be considered random because it's really a turbulent fluid that you have there, the wave is really, the sea is really turbulent, what is the probability that within a given time you will get a rogue wave that emerges of it? Okay? You can mathematize this, and as I was explaining on the previous slides, you can reduce that to an optimization problem, which is that you can ask yourself, what is the most likely way, or rather, the least unlikely way this rogue wave will appear out of this average, state, okay, random state. And if you do that, you can actually identify this state. So what you can do is you can compare these things. So this is space, this is off scale. So this is space, but this is 5 kilometers of the sea. This is time in minutes, and this is the height in meters. Okay? And what you can see is that, well, if I pick randomly, looks like a typical state of the sea, and I evolve it in time, well, typically I don't see any rogue wave appearing at that, in that location. It just goes. I think Lelia is a little bit scared by the rogue waves. Sorry about that. They are quite scary, I have to say. So you see that it's okay. I'm going to survive this one. Don't worry. So you see that typically nothing happens. You see something which essentially looks more of the same. But if you take specific initial condition, you can create these rogue waves. And here is one that appears here. Okay? And then you can ask yourself, well, it's an optimization problem. You can actually ask, well, is this, you can ask it, well, you can use this framework then to first assess, is this the only way rogue wave can occur? Right? And the answer is yes. In other words, you can do something which is, instead of doing this optimization that I'm talking about, which is to try to find what's the most likely way or least unlikely way for the wave to occur. Instead of doing that, I can just repeat the experiment many, many times and see when a rogue wave occurs. And then when the rogue wave occurs, I can ask, well, does it happen in a, I've done that by brute force, no, in a very kind of, stupid way, if you wish. Is the rogue wave that I see by this repeating experiment essentially similar in feature to the one that I had calculated as being the least unlikely? And the answer is yes. You can do this calculation, meaning that you can, and this is what this shows, these are snapshots at different times, where you can see that this is the elevation of one of the curve here, the black one, that you see evolving in time, is the elevation of the sea that is the most likely to create a rogue wave. And then around that, you have essentially a cloud, which is what are all of the waves that essentially create, starting from this initial condition, that will create this rogue wave. And you can see that they all fall into a very thin band. Okay? So that means that you can bypass this calculation of doing, repeating the experiment and just try to find what is the most likely state of the sea that will create a rogue wave. Okay? And once you have that, you can calculate the probability of having rogue waves out of the initial condition. That's not very important. It just tells you that, well, they are not as unlikely as one might think, but it allows you to quantify that. But maybe more importantly, and this is what I was discussing about this early event detection, what's important here is that with this type of methods, you know that if what you see is this, well, you better either run away or try to turn your tanker in the right direction, because that will create that within 20 minutes. And there is no way around it. Well, you might, that's detection. You might try to control the sea. That's much more complicated. I would not know how to do that. But certainly it will tell you, I know now, what is happening. And if you see this, then it's even more likely, but it will happen after 10 minutes only. Okay? So this allows you to detect things before they occur, right? And, well, this is a simple example. I should, not kind of mislead you. This is a simple example in the sense that why is it simple is because it's done with a mathematical model, which, as mathematicians do, is just a model of the sea, not the real sea, right? If we had models which were satisfactory for hurricanes, for example, or drought, or, precipitations, rain, then we could do the same thing. But there the problem is in the model. But certainly this is a direction in which, scientists are going and will certainly in the coming year allow you to predict better, right? You would see, if you see the occurrence of this in the emergence of a hurricane, you know that it will be a bad one. And that would allow you to better make prediction and therefore, to tell people evacuate because there's going to be, a bad one. Okay? If you want to see what they do, I mean, these movies are not so, but this is the way they evolve in time and focus. This is not very illustrative. It's just showing you the wave appearing. It is also showing you, as you can see, so this is, the movie is in a loop. It starts with the state of the sea, the most likely one, and then it goes into this wave where you see that there's a triple that I was talking about, right? And you need to remember, again, this is completely off scale because it's 5 kilometers here, but only 12 meters here. So at the end, this is not very big. And you can make this calculation for much bigger waves, but then the brute force calculation become a little bit more complicated. Okay. So that's pretty much half of the story I wanted to tell you, and that's about, rare event, extreme event detection. And I hope I conveyed to you the fact that you can use certain mathematical tool combined with the right physical model to, make some prediction about that. Right? Now I'd like to switch gear a little bit and to talk about the other part, which is this protein folding. In fact, I'm not going to be really talking about protein folding, but I'm going to be talking about rare events which are, in this context, rather called reactive events in molecular biology. Right? And so the beginning, and here, as what you see here, and I'll get to that in a minute, these are just artist impression or molecular dynamics in some cases, but of protein in your body. I'll get to that in a second. So what is fascinating about biology, in a way, right, is that a living organism like yourself or everybody else in the room or other animals right, are built, as I explained at the beginning of the talk, in a way which is quite different from the way you would build a machine. And that's actually because they are built by evolution rather than by an engineer. And in particular, what they do is that they typically operate in a very noisy environment. If you go down in scale to, to the cellular level and then down inside the cell and you start to look at molecular level what is happening in your cells, what's happening in there is a bit of a mess. I mean, it's really something where there's a lot of fluctuation. There is a lot of trial, error, failure, things like that are going on, right? But even though, as a machine, at molecular level, everything is essentially governed by randomness, these, once you put them all together, form individuals, living organisms, that are very reliable and functional. Okay? And the question is a little bit, how does that happen, right? And why does that happen? And okay, so what I want to explain is, in particular, that macromolecules like proteins, which are really the workhorses of your cells. This is the one that do the job. Like, this is the few examples here are actually very, important. So this one is aquaporin channel. This is the one that control the way you can, these are ion channels that you have at the membrane of your cell that control or water goes in and out, but also potassium, sodium, all the kind of, minerals that you need to have in the cell. These, and we're going to focus on that later, is a kinesin motor protein. So it's a little protein, right, that walk on the track, and which is such that it brings organelles in your cell from one part to the other. If you were to wait for diffusion for that to happen, it would just take too long. So there are tracks in your cells, and there are these little guys that are walking on these tracks and that are carrying things around where they are needed. It's a very simplified picture of what is actually going on, but it's also somewhat a faithful one. It's really, this is ATPase. That's the most probably basic phenomenon that happens in your body, is the way, because ATP, as you know, is your fuel, right? And so it's the way you actually use the oxygen that you have and nutrition, etc., to go from ADP to ATP that can be then used as source of energy. They are the one, in fact, that are then used, for example, by these molecular motors here to make them work. Okay? And that's another type of molecular motors, which is just to show the scale involved. That's the one that makes the flagella of a bacteria rotate. If you go, the flagella is small, but it's quite big compared to, there's a little machine in there that actually makes it rotate so that the flagella, well, that's for the, the one that are like screwdrivers, right? And so how does that happen? Okay? And so what is happening at this level is that this machine, right, as I said, don't operate in the same way as regular machines operate, in the sense that they take advantage, since they are in a thermal environment, which meaning a fluctuating environment, they take advantage of that. And they take advantage of the fact that there's a huge separation of time scale between which certain phenomena can occur in the cell and the time scale in which they are needed for the cell to operate. Okay? And so let me try to explain that. So first of all, one thing that is important is that when you look at molecular biology, the structure and the shape of protein is related to their function. So the way really their shape is what makes them, operational or not. You probably know that they need to fold, for example. They are not built folded, they need to fold. So that's, Okay, so one question is how to do that. And typically, when they do some function, the way they operate is, okay, so let me explain that. Typically, if you have a bag here that you'd like to bring on the other side of the mountain, right? What you would do, what one would do here, is that you would, drive it up to the saddle point somewhere, like, you would go up the hill, and then either you would drive it down or you'd let it roll. That's the way you would have to push it over the hill, okay? This is not the way molecular machine operates, because there's another way which is simpler, which is what they do is that they just change the shape of the landscape. Meaning, when this valley is lower than the one next door, typically it's more stable to be here because it's deeper. That's where things are happening. The way you would like to bring it on the other side is simply you change the ratio. You make the other value a little bit deeper. And then you just wait that the thermal fluctuation will bring your luggage or whatever, your cargo, on top of the hill. And the reason why you can do that is because the ATP, ADP that make these changes typically operate on a very fast time scale, right, femtosecond or the like, right, which is 10 to the minus 15. It's extremely fast. And then you can just wait forever on that clock for things to happen, right, and that will still be very fast for your body. If something, if your clock is the femtosecond, which is 10 to the minus 15, 0, 15, 0, and then 1, right? A microsecond is like enormously long. The microsecond for you is very fast. So anything, that didn't operate on a microsecond timescale, you can actually do it this way, using the thermal fluctuation, okay? And so that, that's the general picture, in fact, that you see also in chemistry book for enzymatic reaction. They're typically more complicated than that, because what it means is that you are in a landscape like this, and this is where the system was, and then you change the shape of the landscape to allow him to have a thermal fluctuation to push it over the hill and go to the other side, from the reactant to the product. There are many other ways to do that. You could also lower the barrier at the same time, etc. The difficulty is that this cartoon now needs to be related to the reality, meaning to the model that you have for this protein, for example. In the devil of in this data, that's a nice picture, but every protein in your body has a different function, right? And so if you'd like to understand this function in the detail, then you need somehow to understand this mechanism at the molecular level of the protein. And that's much more complicated to do, because if you think about this system, they are very complicated. They involve many, many molecules. One protein, which is a huge molecule, involves many, many atoms that can all move independently, well, not really independently, but in concert with one another through a force field. That's what molecular dynamics simulate. And you'd like to understand, how these guys all together perform these functions, okay? And so the way is to picture that is really to try to picture a navigation over an extremely complicated landscape, like, with many, many different hills in much higher dimension than the one we are used to, right? And so this is like, trying to find your way onto rugged landscape like this, where there's, if you do hiking, that would be a different landscape to navigate upon, because you don't see the valley, you just see little saddle points, and if you go to one, there's another valley, and then you don't know that the paradise you like to go to is actually over here, right? But it's also like another picture that you can have in mind is really navigating in a maze. Okay, so how do you organize these mazes to actually, manage to bring, this little random walker that is in the maze in a way from entrance to exit, which would be from, from a reactant to a product, or from one state of the protein to another one. How can you manage to do that? Okay. And so I'll explain, maybe one application of that to conclude, which is work that was done. In fact, it was done in collaboration with Martin Karplus, who is a computational chemist who got the Nobel Prize a few years back for his work in molecular dynamics. I mean, not this work, the development of the whole scheme. So that's just one application of this. And this is about molecular motors that I introduced before. Okay? And what we did here, in a nutshell, I don't think it's very useful to go into the detail, but is try to understand how these molecular motors work. So remember, these are the guys that are working on the tubules, right? So how do they do that, right? So how do they work on this actin filament, right? And so they're really like, if you look at their shape, they really have like two legs that go, right? And they translocate, meaning that one detach and then it attach in front, and then this one detach and reattach, and it does that. Okay? And the way it does it is that, well, again, if you were to build this machine, right, what you would typically do is that when it consumes fuel, you would make it make a step. Okay? But the way biology has designed this machine is not like that. What it does is that what it does when the ATPase occur, when it uses fuel, it just detaches from this position on the track and make attachment on that guy, the position ahead, a little bit more likely. Meaning that from time to time it will reattach where it was, but most often than not it will go one step further. And then this process repeats. And the way this process is happening is that part is just thermal fluctuation, because at that level you don't need fuel anymore. Okay? These are not perpetual machines, don't get me wrong. Right? You need fuel. They would not work just due to thermal fluctuation. But they use the thermal fluctuation in concert with the fuel to do things efficiently. Okay? Or, I mean, the way it was designed. Okay? And so you like to understand how that happened at molecular level, and so you can use the tool, which is the tool that for which he and two other guys got the Nobel Prize, which is that you can just simulate, make models of every single atoms that there is in these molecular motors and see how they move in concert by using complicated force field. So it's essentially looking at F equal ma, going back to Newton, right? But looking at that for a very complicated system subject to thermal fluctuation, like Boltzmann told us to look at, because they are thermal fluctuation. And if you do that, you can do this simulation, and you can actually, I mean, this is what is called, rub and twist representation of these molecules. You can actually understand the pathway, meaning what exactly is happening. How do they go over the hill to go from here to here? What is exactly happening in the molecule? What are the sequence of steps that they take that allow them to perform this step explicitly? And the interest of this thing is that it gives you really a microscopic picture of the way these molecules operate, which is good for first principle understanding of what is going on, but also potentially would allow to control or even design machine of this type. In this specific case, the way that we did, explain why in the experiment you saw sometimes that the step seemed to be smaller than it had to be, right? This was something which had to do with this pathway, okay? And I mean, this is just one example, but there are many other examples of molecular proteins and other protein docking, etc., that can be understood using the same type of framework. That's the whole realm of molecular dynamics, which is becoming more and more successful and powerful to do this type of calculation. Okay, so I'm pretty much done. I mean, I just want to give you a bit of an outlook, right? So what I try to explain to you, I hope in simple terms, is that if you combine statistical mechanics, this tool, with the mathematical tool from probability theory, you can, in fact, try, and sometimes succeed, to explain the behavior of systems that are too complicated to be described in detail, where only a statistical perspective is useful. And I try to illustrate that on two things. One was how to estimate the probability of occurrence of extreme events, right? And well, I discussed rogue wave because I was focusing on problem from geophysics, but clearly there are many, many other instances where this type of framework are useful, like, for example, in the case of earthquake or hurricane as well, but also pandemics and so on. I mean, any type of these events which are rare when they occur, but when they do, they're really bad. There's another whole area where this is kind of important, is the area where you have engineering of components that will be extremely reliable, like your computer, your car, but also the component that you have in aerospace or in medicine, where you really don't want your plane to fail. So you'd like to understand what's the mode of failure that they would have, and it might be quite difficult to do experiment with that because these events are so rare. So if you have models that allow you to bypass this experiment, it's actually a good thing. Okay? And then there was kind of a parallel story or complementary story, which was to show you that the same type of ideas can be useful in cases where these extreme events or rare events are in fact not that rare on the clock of the system, and they're in fact ubiquitous, and that's why the system works. And I try to explain that with an example from molecular biology, but there are many other instances like hydrodynamic and turbulence, optimal control. There are we are more and more designing machines that operate at the nanoscale, where thermal fluctuations are important. So you want to know how to operate them. If you want to try to do a Carnot engine But at the nanoscale, it's not like the Carnot engine. It will be different from the engine that we have. And there are other things like active matter, which are more the one that are being discussed in the conference that is happening right now at the Aspen Center for Physics. And with that, I thank you for your attention.
So, thank you very much. And we have time for a few questions for Professor Vanden-Eijnden. So, is anything on your mind about, I see a question in the back there.
Yeah, I have one. Basically, when you look at these sort of rare events that you want to be able to predict what's going to lead to it, how do you know what sort of dimensional space is important, right? Your rogue wave, it was pretty easy, but for some of these other things, the failures of components or whatever, how do you decide what phase space you want to operate in? What's important to measure and look for?
Okay, so I repeat the question. Right? So what's phase space is important to describe the events and how, right? So okay, this is a very good question. It's a very important one because this essentially, is related to the fact that when you want to predict rare events from a model, if you want the prediction that you make to be relevant not for the model, but for the reality this model is supposed to represent, you better be sure that your model is realistic. Okay? And that is a modeling issue, which is a non-trivial one. Fortunately, there are many systems in which we know that, because if you go to the most basic level, well, you go back to essentially the equation of Newton. For the rogue wave or things like that, typically that's too far, but there are other models like Navier-Stokes, equation for fluids that are the one that are typically relevant. And with the advent of more and more powerful computer, right, you can actually use models at a level of precision where you know that they are accurate to start to do this calculation. But that remains an issue where you need to be careful into what you do. The advantage of using technique like the one I described is that if you can reduce the problem to an optimization problem, which is trying to find only the most likely way by which the event occurs, you can simplify your calculation, meaning it's less costly to do. I hope that answers your question. Yes.
It's kind of a simple question, but when you did the brute force examples of the rogue and then the middle and then the beginning,
Yes.
and you said the rogue wave stems from the very beginning you could determine, is that sequence, the very beginning sequence, always going to determine a rogue wave?
Sorry, I didn't hear the last part of the question. Will it?
The beginning sequence, will that always determine a rogue wave, or can you have that sequence and not end up with that rogue wave?
Okay, so the question is whether the specific initial condition will lead to a rogue wave. So that's really what these calculations were confirming, that indeed, in that specific instance, because it's an extreme event, there is essentially only one way for it to occur. Meaning, this initial condition, if you see it, will produce a rogue wave. There is no escape, right? It's a I mean, and I didn't go into the detail, but the structure of this initial condition is actually quite complicated. It's a field, so you need to describe a shape of the sea on many different scales. There are many features in there, and they are important. If you see that, it will create a rogue wave. There was another. Yeah.
So I'm just a bit confused. I'm not sure what I learned. So here's the question that
Okay.
actually relates to that. So I think what you're describing as initial conditions are an input,
Yes.
and a transfer function or a model, and the convolution of those two things, and then you get an output like the one you just described. So does it not? I'm not sure where you're applying the probability. The initial conditions are very complicated in a rogue wave. I mean, waves everywhere. The model of the sea is incredibly complicated, and doing that math is incredibly complicated, the convolution. So where is it we're doing probability? To all three, to just one of the three?
Okay, so
you said with the same initial conditions, they'll all come out the same way. That's assuming that your model, that's your transfer functions, unchanged each time.
Yeah, so the question is, where is the probability coming around? I mean, where does it enter the description if you have an initial condition which is complicated, and then a model which is complicated, and you combine the two. Okay. So in this specific case, for that specific example, and you know, the answer may vary from case to case, but in this specific case, the rogue wave, one takes is that the randomness comes from the initial condition. Meaning, so I skipped this detail over a little bit, but there are many experiments that are being done where people record the state of the sea in different wind conditions, for example. Okay? And what they do is that they can tell you what's the spectrum of the, so you know, there's different length scale or wavelengths, right? And there's certain energy in all of these wavelengths, and they can measure that. Right? That's the measurement that they have. And so if you use kind of some form of Bayesian inference, you can say, well, I can take that and turn it into a random initial condition. I can say, you know, I have random, this is a turbulent, it kind of is, it never, if you look at the sea, it changes all the time, right? But I take as an input, as a prior, if you want to take a Bayesian perspective, the random, you know, I build the random initial condition based on that. And then the model is deterministic. So the randomness comes from the initial condition. I mean, when you do, you know, this is exactly what is being done when, you know, when people, when you have the weather, you probably know that, but when you read your weather report, and it says 50% chance of rain, right? It is the same idea, which is that people say, well, I'm measuring the state, you know, of the weather right now in Aspen and the surrounding, but when you do that, you can only resolve it at a certain scale, which is, you know, what are the stations that you have to measure the wind, the temperature, and all that. And so you need to build an initial condition on that which contains more information that there was in, right? And so the right way to think about it is to say, well, there's an error. There's all what I have not seen. I'm going to build statistics upon this, right? I hope that this error is small. I mean, that's the precision of the measurement. But since my system is chaotic, and that's the case for the rogue wave as well, when it evolves from it, right, this small randomness will create different outcomes. Same ideas. Okay? There's a question in the back, I think.
Is there diagram where you describe protein folding, you had the landscape, and you said you changed the landscape to change the way the protein folded, I think. And then, but in the example of the machine that was stepping forward along the track, it seems like the ATP coming in not only changed the landscape and increased the probability of the step going forward, but also changed the protein directly itself.
Sorry, I didn't hear the last.
It seems like the ATP not only increased the probability of the step going forward, but it also directly impacted the way the protein is folded. So it seemed like it did both features, not just change the landscape.
I mean, in this specific case, you can really think about it as changing the landscape. When the ATPs occur, you know, not ATP, when the ATP is consumed, right, that changes the shape of the protein, which is, it changes force, it really changes the landscape. So it pushes it in a slightly different, and then the rest is just thermal fluctuation. That is really the way. You know, there are many other phenomena that arise in the same way in your body. I mean, one other example is the way oxygen is delivered by hemoglobin. There is also, at some point, there is a change. There's something which detaches that requires energy, and then the rest is similar. The landscape has changed, and then it can escape. But it's not like, from a viewpoint of, you know, of efficiency, right, it would be too costly, and it's not necessary at the molecular level, as I explained, to just push the whole molecule on the other side. It's not necessary to do that, because you would consume an enormous amount of energy to do that, which is available by the thermal fluctuation as long as you have, you know, put the right balance for the landscape.
But presumably the ATP has some effect on the protein, whether it attaches to that spot or not. So,
right, but that's part of the landscape. I mean, right, so the ATP has an effect on the protein and the way it attaches. That's part of the landscape, right? The way we think about this is that the whole system needs to be thought about one landscape here, right? And in fact, in the molecular simulations that are done, you know, there, we cannot at this point in time simulate the whole system. So we take a sub-part of it, and we simulate that, right? And we take it after this ATP, the ATP has been consumed to see what happens subsequently. Okay?
Time for one last question. And, yes.
So for all of these systems that you are simulating, you are like knowingly leaving some gaps in the system, like you saying, okay, we're just going to have the simulation do that part without knowing what exactly causes that, so we can understand more about it and then get to that level of detail later. That's what I pulled from what you just said there. Is that true, false? Are you trying to get as much granularity in your simulations as possible?
So the question is whether I try to have as much clarity in the simulation as possible. What we try to do here, and for the first class of example, is really to assess the probability and the pathway, meaning the mechanism, by which certain extreme event can occur, either from imperfect knowledge about the initial condition and or imperfect model. That's one class, right? And so it's really assessing probabilities and mechanism. The two go in concert, actually. And the other class of system is really trying to understand at a more fundamental level how these machines operate when they operate in this environment where the randomness of the environment itself is crucial. It's not something which is detrimental to their functioning. It's something which is crucial to their functioning. So you'd like to understand how that works. I mean, this is, we still, at this point in time, don't really understand. We understand general mechanism for this, but we don't understand in the detail how this is happening. And when I say in the detail, is we would like to be, we would like to be eventually able to engineer machines that do that self-assemble, for example, the same way protein fold. And there are many, the conference happening this week at the Aspen Center for Physics is about that, in fact. And there's a lot of progress that has been done in this area, but there's still a lot to be done. It's a very exciting time, actually.